Hello everyone, this is Nikilian, Assistant Professor, Department of Civil Engineering, AJT Mangalore. So today I am making this video to tell you about losses in prestress. So what is losses in prestress? In prestressed concrete members, the most important parameter is prestressing force. If the prestressing force reduces with time, then obviously the prestresses also get reduced. So even at the time of transfer of prestress to the concrete member, there are chances of reducing the prestressing force from the recorded value as per the jack gauge. The various reduction of prestressing force are called as losses in prestress. So this loss of prestress will affect the stress distribution of the member. Therefore, it is said that the losses that may occur in the member due to various parameters should be examined carefully, and the required pre-stressing force has to be provided. Now let us see what are all the losses that may occur in the pre-stressed concrete members. So here the losses can be divided into two categories. One is immediate loss and time dependent loss. So again the immediate loss is further divided into three categories: elastic shortening, friction, anchor slippage, and time dependent loss is further divided into creep, shrinkage, and relaxation of steel. So immediate losses means these are the losses which will occur within a short duration after the construction, and a time dependent means the losses will take long time to come into the existence. So it is called as time dependent loss. So here in this slide you can see losses encountered in pre-tensioning and post-tensioning system. So you all know what is pre-tensioning members and what is post-tensioning members. So pre-tensioning members means here the tendon or a cable is tensioned first and then the concrete is placed. Whereas in post-tensioning the concrete is placed, and after the concrete member gains its strength, the cables are passed through the ducts which are provided within the concrete member, and then the cables are tensioned and it is anchored at the ends. So this is the difference between pre-tensioning and post-tensioning members. So what are all the losses that will occur in pre-tensioning members, and what are all the losses that will occur in post-tensioning members? First I will consider pre-tensioning members. In pre-tensioning members we have four losses. First one is elastic deformation. So there is a loss of pre-stress due to shortening in the length of a concrete, which is also called as elastic deformation or a shortening of concrete. Second one is creep of concrete. So there is a loss in pre-stress due to creep of concrete. There is a loss in pre-stressing force due to shrinkage of concrete, as well as there is loss in pre-stressing of force due to relaxation of stress in steel. Similarly, when we consider post-tensioning members, so the post-tensioning members will also experience the same losses as that has been experienced by pre-tensioning members. That is, there will be loss due to elastic deformation, there will be loss due to creep of concrete, shrinkage of concrete, relaxation of stress in the steel. Whereas in addition to these four losses, the post-tensioning members will also experience the loss of pre-stresses due to anchorage slip and friction. So here we can see types of losses in pre-stress. So we have six losses. So the first one is loss due to elastic deformation. Second one is loss due to creep strain in concrete. And third one is loss due to shrinkage of concrete. fourth one is loss due to relaxation of stress in steel, then loss due to anchorage slippage, loss due to friction. So these are the 6 types of losses that will occur in pre-stressed concrete. So before studying about all these losses, the one thing what we need to remember is the total losses should not be more than 20%. So the total losses should be between 15 to 20%. If the losses is more than 20%, then the member is not suitable for usage. So now let us come to the first type of loss, that is loss due to elastic deformation of concrete. So what is elastic deformation of concrete? So here when the prestress is applied to the concrete, an elastic shortening of concrete takes place. So when the elastic shortening of concrete takes place, there is a shortening of tendon length, and the shortening of tendon length is equal to the shortening length of that of a concrete. So this results in loss of prestress. So the loss of prestress in steel is due to its shortening, which is equal to the product of stress in the concrete at the level of Cg of the steel. So here the effect of elastic shortening varies with the length of tendons, whereas if we consider a simply supported beam which is subjected to UDL, in this case normally the midspan section will be under critical section, or the midspan section is considered as the critical section where the stresses are maximum at midspan. So in this case the pre-stress losses are considered at the midspan of the section, whereas in case of continuous beams or continuous span beams, there are many number of critical sections. There are many number of flexural critical sections, or there are many number of sections where the bending is critical. So in this case we will get many number of points where we need to check for the losses of prestress. So here in this figure you can see uh, 4 different members. So the first one is, so this figure shows free tendon. So here in the first stage what we will do, we will increase the length of a tendon, that is a tendon is tensioned by applying a external force. So in the second figure, in this figure you can see the increase in the length of tendon. So after increasing the length of tendon by applying the external force, and remember that the increase in the length is within its elastic limit. So after increasing the length, both the ends, this end and this end, is encouraged by using wedges. So here the formwork is formed in the factory and the cable is placed within that framework. It is stretched within its elastic limit and both the ends are encouraged. So after that a concrete is placed over this tensioned tendon, so that you can see in this figure, in third figure. So concrete is placed over the tendon, so the stresses are transferred to the concrete. Stresses which are developed in the tendon is transferred to the concrete. So in the fourth figure you can see the length of concrete member is been reduced. So it is called as elastic shortening. So when the concrete length reduces, obviously the length of steel tendon or a cable will also reduces along with the concrete. The length of reduction of steel cable or tendon is equal to the length of reduction of concrete. So as a result of this reduction in the length gives the loss. That is, there is a loss of prestress. So how to calculate the loss of pre-stress due to elastic deformation of concrete or loss of pre-stress due to shortening of concrete? So we have two equations, or we have two conditions. So one is for post-tensioning members and one is for pre-tensioning members. So first let us see for pre-tensioning members how how to calculate the loss due to elastic deformation of concrete or shortening of concrete. So that is calculated by the formula delta Fs is equal to mFc. So this is the formula which is used to calculate the loss that is occurring due to shortening of concrete. So here m is nothing but it is modulus ratio or modular ratio, which is given by Es by Ec, where Es is Young's modulus of steel and Ec is Young's modulus of concrete, and Fc is the compressive stresses in steel at the level of Cg of steel, and Fc can be calculated using the formula P by A plus PEI divided by P, sorry, Fc can be calculated by the formula P by A plus PEY divided by I, where P is pre-stressing force, A is area of the cross section, and E is the eccentricity of cable with respect to CG of the section, Y is centroidal distance of the member, and I is moment of inertia. So that is for pre-tensioning members. Whereas for post-tensioning members, we have two cases when all the wires are prestressed simultaneously, then the losses is zero. Simultaneously means when all the cables are pulled together and when it is anchored. In such condition, the losses will be zero. Whereas the second case is the cables are pulled successively. That is, if there are four number of cables, then the cables are tensioned one by one. Then in such cases, the maximum loss will occur when the first cable is tightened, and the minimum loss will occur when the last cable is tightened and anchored by using the wedges. So now let us go to the second loss, that is loss due to creep of concrete. So creep is the deformation of a member which occurs due to external applied stress. The creep strain in concrete is due to the adjustment of particles in concrete and also due to the oozing of water from the concrete and consequent reduction of watts. So here what happens? The concrete, when it is subjected to continuous stresses or constant stresses, the concrete will undergo permanent deformation, or the concrete will undergo irrecoverable deformation, and this is because of flow condition. So this irrecoverable deformation is called as creep of concrete. So creep may also be defined as time dependent plastic deformation under the action of constant loading. In case of prestressed structure, the concrete remain under action of continuous thrust. So this continuous thrust is the result of tensioned steel. Under the action of this thrust, concrete undergoes permanent deformation because of contraction of tension gives rise to equal contraction of tension steel for which there will be loss of stress in the steel. So there are some factors which influence the creep of concrete. So factors which influence the creep of concrete are stress level, strength of concrete, age of concrete at loading, duration of stress, size of the member, atmospheric condition, water cement ratio, type of cement, and aggregates in concrete. So these are the factors which influencing the loss of pre-stress due to creep of concrete. So then how to calculate the creep loss of concrete? So here we can calculate the loss of pre-stress in steel due to creep of concrete in two methods. So first one is when creep coefficient is given. So creep coefficient means it is phi. When phi is given, then the loss of pre-stress due to creep of concrete is equal to phi m fc, where phi is creep coefficient which is obtained from IS 1343/1980, m is modular ratio which is ES by EC, and Fc is the stress in concrete which can be calculated by the given formula, this formula. And when ultimate creep strain is given, then the formula changes. When ultimate creep strain is given, then creep of the concrete is equal to epsilon double C Fc into Es, where epsilon double C is ultimate creep strain for sustained unit stress. Fc is stresses in concrete and Es is the Young's modulus of steel. So we can calculate the loss of pre-stress due to creep of concrete in two ways. That is, one is when creep of coefficient is given and by using ultimate creep strain method. So the third loss is loss due to shrinkage of concrete. So what is shrinkage? Shrinkage is the deformation of the member which occurs without externally applied stress. So the shrinkage of concrete in prestressed members results in shortening of tension wires and hence contributes to the losses of prestress. So here shrinkage means the member is undergoing a shorten in length without loading the member. So the shrinkage is defined as contraction of concrete which occurs due to the loss of moisture or loss of water content during the process of hardening of concrete. So here during the process of hardening there is a process which will occur in the concrete which is called as heat of hydration. So here due to heat generated the moisture content is evaporated. So the concrete loses its water content or moisture content hence resulting in shrinkage of concrete. So shrinkage of concrete depends on various factors. So the factors that is influencing the shrinkage is water content ratio, atmospheric condition and type of aggregate used. As water content increases, the shrinkage decreases. If we consider water cement ratio, with increase in water cement ratio, shrinkage of concrete also increases. And shrinkage increases in hot weather compared to that of cold weather. So how to calculate the loss of pre-stress due to shrinkage of concrete? So we can calculate the loss of pre-stress due to shrinkage of concrete using equation epsilon Sh into Es, where epsilon Sh is equal to 0.0003 for pre-tensioning members, and for post-tensioning members we will use epsilon Sh is equal to 0.0002 divided by log 10 into T plus 2. Here T is nothing but it is the age of concrete and Es is the Young's modulus of steel. So using these equations we can calculate what is the loss of pre-stress due to shrinkage of concrete in pre-tensioning as well as post-tensioning members. So next, coming to the fourth loss, that is loss due to relaxation of stress in steel. So what is relaxation of stress in steel or relaxation of steel? So whenever steel is held at a constant length in a tensioned state, what will happen? It loses its pre-stress with passage of time, and this phenomenon is known as relaxation of steel. So here the relaxation of steel depends upon various factors such as intensity of stress, distribution of stress and type of steel employed. If the intensity of stress or intensity of loading is more, then relaxation of steel will be more. If duration of stresses are more, then relaxation of steel will be more. If good quality steel is used, then relaxation of steel is less. With moderate or poor quality of steel, then the relaxation of steel will be more. So the value of relaxation loss varies with type of steel, initial pre-stress and age and temperature. So here we can calculate loss due to relaxation of stress in steel using equation delta Fs is equal to Kfs by 100, where K is pre-stressing loss due to relaxation in percentage and Fs is the initial pre-stress. Now coming to anchorage slip, loss due to anchorage slip. So loss due to anchorage slip occurs only in post-tension members. So why this losses occurs is because, so let us consider this member as a post-tension member. So here in this member the concrete is first placed. So concrete is placed by providing a ducts which facilitates for the passage of cables or tendons. So after the concrete gains its strength, the cables or tendons are made to pass through this ducts. So after the cables are passed through the ducts, the cable is fixed at one end. The cable is fixed at either this end or it is fixed at this end. So in other end where the cable is free, it is pulled by using external jacks and it is tensioned. So after tensioning the cable as per the design requirement, the cable is anchored by using the wedges. So during this process, during the process of anchoring the cable using the wedges, there may be a slippage of the anchorage. So practically there will be slippage of anchorage for some length. So due to this slippage of the anchorage, there is losses in the pre-stress of the steel and it is called as loss due to anchorage slip. So the loss of pre-stress in steel due to anchorage slip can be calculated by the formula delta Es by L. So delta is anchorage slip in millimeter, L is length of cable in millimeter and Es is modulus of elasticity of a steel. And lastly, loss due to friction. So this type of loss will also occur only in the post-tensioned members. So friction means it is a contact between two different surfaces or between two different bodies. So if I consider pre-tensioned member, there the cable is tensioned first and then the concrete is placed. So there is no question of two bodies coming to the contact, or there is no question of pulling of a cable which will come in contact with the concrete. Whereas in case of post-tension members where the concrete is first placed and then the cables are passed through the ducts. So here what will happen when a cable is pulled from the one end. So for example, consider a rectangular beam. So in a rectangular beam, let us consider a duct is provided for a passage of a cable. So let us consider that the duct provided is curved. So this is the duct provided. So the cable or a tendon is placed through this duct. So let us assume the cable is fixed at this end and this end is free. And now we need to impart a tension for the cable and we need to anchor the cable using the wedges. So for this purpose what we will do, we will apply the tensile force at the free end by using jack. So while doing this, what happens, the cable will come in contact with the surface of duct which is provided within the concrete member. So as a result of this, friction is developed. So due to this friction, there is loss of prestress in the steel. So here you can see the cable is coming in contact with the duct which results in the loss due to friction. So the ducts are either straight or it can be curved profile depending upon the design requirement. And now how to calculate losses due to friction. So loss due to friction can be calculated using an equation Fs into mu alpha plus Kx, where Fs is pre-stressing force at the jacking end and mu is coefficient of friction between concrete and steel which varies between 0.25 to 0.55. Alpha is the cumulative angle in radian through which the tangent to the cable profile has turned between any 2 points under consideration. So here you can see this is alpha. So it is a curved duct and the cable is passed through this duct and the cable is subjected to tensile force at this end. So as a result of this, the cable is coming in contact with the duct at this point and an angle is developed. If we draw a tangent with respect to this surface, we will get an angle and that angle is called as alpha, which is a cumulative angle, and this angle is considered in terms of radian. And K is frictional coefficient for wave effect, which varies from 15 into 10 to the power of minus 4 to 50. E is equal to 2.7183 and X is the length between X and O. So X is the length from this end to this end. And now how we can reduce the losses due to friction. So losses due to friction can be reduced by taking some precautionary measures. So what are those measures? Passing the cable through metal tubes at the ends. So if we see a post-tensioned concrete member, at the ends these concrete members are not provided with a metal tubes. So if we provide a metal tubes at the ends of a concrete member and if we allow the cable to pass through that metal tubes, then we can reduce the loss due to friction, then making the bends as small as possible from end to end. So with the increase in the bend, there is increase in the loss due to friction. Hence, we should provide a bends as much as minimum, making the radius of curvature at the bends as large as possible but not less than 800 times the diameter of the wire. So the radius of curvature at the bend should be more and the diameter of this curvature should not be less than 800 times the diameter of the wire. So avoiding double curvatures. So this depends upon the importance of the member. So in some members it is required to provide a cable profile with different eccentricity depending upon the loading condition. So in such cases we may have to provide single curvature or we may have to provide double curvature or triple curvature. So we should try to avoid double curvature as well as triple curvature. So with the increase in number of curves or with the increase in number of curvature, there is increase in the loss due to friction. So supporting the cables at clear interval. So by supporting the cables inside the ducts will reduce the contact between cables and the duct so that the friction loss can be reduced using lubricants for unbonded cases. So use of grease or oil can also help in the reduction of loss due to friction. So pre-stressing the wires from both the ends. If the wires are pulled from both the ends, the wires are pulled from this end as well as this end simultaneously, then we can minimize the loss due to friction. So these are the different types of losses that will occur in pre-stress. And now let us go to the second part of the same model, that is a deflection of pre-stressed members. So what is a deflection? So deflection means it is change in the direction of a member. So why the direction of a member changes? The direction of a member changes because of the loading condition. So deflection. The deflection is calculated for the service loads. Since a prestressed concrete member is smaller in depth than an equivalent reinforced concrete member, the deflection of prestressed concrete members tends to be larger. Hence, the calculation of deflection becomes necessary when the members are shallow. So here, the calculation of deflection for prestressed members is mandatory because if we consider the cross-section area or if we consider the thickness of prestressed concrete members and reinforced concrete members, we will come to know that the thickness or cross-section area of PSC members are less. Therefore, the deflection may be more in this case. So it is mandatory to determine the deflection of prestressed members when the members are having very less depth or when the members are shallow. So how here we let us see how to calculate the deflections for different cable profiles and why we need to calculate the deflection, all these things. So necessity of deflection control. So as I told you, if we compare the section of PSC member with RCC member, the thickness of PSC member is less. And here the main thing is the deflection should be within the limit. So why we need to control the deflection? What is the necessity of controlling the deflection? So the necessity is excessive deflection may lead to sagging floors and roof that do not drain properly. So if the deflection is more, the floor will be under sagging condition. So if the floors are under sagging condition, then the water may not be drained properly. So when the water is not drained properly, the stagnant water may cause damage to the member. So excessive deflection may cause damage to partitions and finishes. So if the deflection is more, it may cause a damage to the partition walls and for finishes like false ceiling and other things. Large deflections under dynamic effect and under the influence of variable loads may cause discomfort to the users. So if we are sitting in the first floor or a second floor and the floor which we are sitting is having a large deflection, then we will experience discomfort while moving on that floor. Hence, it is necessary to control the deflection. Then, sagging of a structure due to excessive deflection will make the member appear unsightly from architectural consideration. So, if the member is having sagging position or if the member is under sagging condition, then the aesthetic view of that member will not be good. It looks very odd. Then excessive deflection leads to creation of pools of water on road surfaces of bridges and other associated structures. So if prestressed concrete members are used in the construction of bridges, and if these bridges undergo large deflection, the water which is coming on the bridge during a rainy season or during the overflow of the river, the water will not be drained out properly. So this water will stand on the member, which causes water pooling on the member and creating damage to the structure. Now let us see what are the factors influencing deflection. The first factor which influences the deflection is self-weight of the member and imposed load. So with increase in the load, there is increase in the deflection. With decrease in the load, there is decrease in the deflection. Magnitude of pre-stressing force. If the magnitude of pre-stressing force is less, then the deflection is more, because if the magnitude of pre-stressing force is less, then the upward thrust or upward force that is exerted by the cable will be less, and as a result of this there will be deflection. Cable profile. So cable profile should be properly provided. So if we provide a cable profile as same as that of bending moment diagram, then the deflection and the bending moment will be 0. On geometry of the section of the members. So geometry of the section will also play an important role in controlling the deflection. Modulus of elasticity of concrete. If the modulus of elasticity of concrete is more, then deflection is less. With a decrease in the modulus of elasticity of concrete, deflection increases. And shrinkage, creep, and relaxation of stress in steel increases deflection. Span of the member. So with increase in the span, there is increase in the deflection. With a lesser span, the deflection is minimum. Support fixity condition. If the support is fixed, the deflection is minimum. If the support is hinged or pinned, we can experience more deflection. So why deflection occurs in a member? So it may be a slab, it may be a bridge, or it may be a beam, anything. So why these members will experience a deflection? So deflection occurs due to prestressed cable, due to live load, and due to dead load. So the beam is said to undergo deflection because of these three things. One is due to prestressed cable, due to live load, and due to dead load. So first let us see how the member is undergoing deflection and what is the amount of deflection that will undergo due to the prestressed cable, and how to calculate the deflection due to prestressed cable. Yes. So deflection due to prestressed cable. So prestressed cable. So we can provide a cable with different profiles. So cables can be straight, it can be curved, or it can be linear. So here first let us see deflection in beams with straight cable or tendon. So here you can see a rectangular member. So to this rectangular member, a cable is provided, and the cable is a straight cable. So due to this is the bending moment P into E, where P is the force, that is prestressing force, and E is the eccentricity. E is the eccentricity. So eccentricity is the distance between CG of a member and a cable. So here you can see the eccentricity E. So we have a relation, moment is equal to eccentricity into force. So bending moment, this is the bending moment, this is the bending moment which is obtained from eccentricity into force, pre-stressing force. So to calculate the quantity or amount of deflection, in this case, the deflection is equal to moment of area of BMD for half span about the support divided by flexural rigidity. And if we take the moment of area of bending moment diagram at half of the span, then we will get delta is equal to PEL square by 8EI, where P is pre-stressing force, E is eccentricity, and L is length of a beam, and divided by 8EI. EI is modulus of rigidity, E is Young's modulus, and I is moment of inertia. So deflection in beams with drapped tendons of trapezoidal profile. So here we can see in previous case it was a straight cable. The cable or a tendon was straight, but here a tendon is having zero eccentricity at two supports, and it is having eccentricity of E at midspan, and the cable is having a trapezoidal profile. So here you can see, so for this type of cable profile, the bending moment will be like this. So this is the bending moment diagram. So to calculate the deflection of this member, which is having a trapezoidal cable profile, deflection is equal to same formula, that is moment of area of BMD for half span about the support divided by flexural rigidity. That is delta is equal to PE by EI into 2L1 square plus 3L2 square plus 6L1 L2. So L1 and L2 is shown here. So from here to here it is L1, and from here to here it is L2, and this is E, the distance between CG of the member and the cable. So this is the deflection of a beam when it is provided with a trapezoidal cable profile. And next let us see deflection in beams with parabolic tendons. So parabolic tendons means the cables are curved cables. So what will be the deflection when a curved cable is provided? So here you can see in this picture, so a rectangular beam is provided with a curved cable which is having eccentricity of 0 at both the ends and eccentricity of E at midspan. So for this, the bending moment diagram is this one. So we know that moment is equal to force into eccentricity. So here the force is 0 at both the ends. At both the ends the eccentricity is 0 and the force is P. So P into 0, it is bending moment is 0, and at the midspan eccentricity is E and force is P. So P into E, it is PE at the midspan. So the deflection when curved cable profile is provided, delta is equal to 5 PEL square by 48 EI. That is the deflection of a beam when it is provided with the curved cable profile, when the cable is having zero eccentricity at the ends and eccentricity of E at the midspan. So next, deflection in beam with the parabolic tendon or a cable with eccentrically anchored. So here also the cable or a tendon is having a curved profile, but in previous case the two ends were having zero eccentricity, whereas here the cable is having an eccentricity of E2 at supports. So here you can see the cable is having eccentricity of E2 at the supports, and eccentricity of a cable at midspan is E1. Here it is E1. So for this is the bending moment diagram. So this is the bending moment diagram for midspan, that is P into E1 plus E2, and this is the bending moment diagram for the eccentricity at the ends. P into E2, P into E2, and it is P into E1 plus E2 for midspan. And for this case, the deflection of a beam delta is equal to PL square by 48 EI into 5 E1 minus E2. So using this equation, we can calculate the deflection of a beam when the cable profile is having eccentricity of E1 at midspan and eccentricity of E2 at supports. So the next case, deflection in beams with sloping tendons and eccentrically anchored. So here it is a linear cable or a sloping cable or a tendon. So here you can see at midspan the cable is having an eccentricity of E1, and at the supports the cable is having an eccentricity of E2, E1 and E2, and the pre-stressing force which is applied at both the ends is P. So to calculate and to draw the bending moment diagram for this condition, we will use P into E1 plus E2. So this gives bending moment diagram at the midspan, and for the end supports the moment is P into E2, P into E2, that is eccentricity into force, we will get moment. So that is shown here for supports. So for this case, the deflection delta is equal to PL square by 24 EI into 2 E1 minus E2, where E1 is eccentricity at the midspan and E2 is the eccentricity at supports. And the next case is deflection in beams with parabolic and straight tendons concentrically anchored. So in previous slides we saw that the cables were parabolic and the cables were linear, but here the beam is provided with both. For some length the cable is linear and for some length the cable is parabolic. So here if you see here from here to here the cable is this, in this portion the cable is parabolic, at L1, and the cable is linear in the from L1 to this point. So from here to here it is parabolic and it is linear here. So in this condition, what is the deflection of a beam? In this condition, the deflection of a beam is calculated using this equation, where L1 is the length from the support to the point where the direction of a cable changes, and L2 is the length from the point where the direction of cable changes to the midspan. Next condition is to calculate the deflection in beams. To calculate the deflection in beams with parabolic and straight tendons eccentrically anchored. So this is same as previous one, but the difference is here the cables is having eccentricity at the supports. In previous case the cables were having zero eccentricity at the supports, but here the cable is having eccentricity at the support. Here you can see the eccentricity of a cable at the support. So here also this portion L1 portion is curved and the remaining portion from here to here it is linear. So this is the bending moment diagram for this condition, and deflection for this case can be calculated using this equation. So that is the equations and different conditions for which the beam will undergo deflection considering cable, pre-stressing of cables. So the second and third thing is deflection due to self weight and imposed load. So it's the deflection due to self weight. So when a beam is provided with UDL, then the deflection is 5WL to the power of 4 by 384 EI, where W is the self weight, L is the length, E is Young's modulus, and I is moment of inertia. When a beam is a cantilever, so UDL with cantilever, UDL means self weight of a member is always a UDL. So when a beam is a cantilever beam, then the deflection is WL to the power 4 by 8 EI. Similarly, deflection due to live load. So when a live load is UDL and it is acting on a simply supported beam, then the deflection is equal to 5WL to the power 4 by 384 EI, and a live load is UDL which is acting on a cantilever, then the deflection due to live load is WL to the power 4 by 8 EI. When a beam is subjected to point load and a beam is supported with simple supports, then the deflection is WL cube by 48 EI. And when a cantilever beam is subjected to point load at its free end, then the deflection of a beam is equal to WL cube by 3 EI. So this is how we will calculate the deflection of a beam under live load, under dead load, and under pre-stressing of the cable.